好，那时间也差不多了，我们开始我们今天的这个 OR Talk。那么首先请允许我再来介绍一下我们的这个运筹 OR 帷幄直播的这个系列。我们现在有3个系列，包括这个 OR Talk、行业 Talk 以及 Tech Talk。那么此外还有一个这个 OR 会客厅，来邀请一些嘉宾来给我们分享一些学习和职业经历。那么这次呢，我们也是邀请到了我们的这位嘉宾叫做曾文耀，大家可以叫他叫 Team。那么来给我们带来今天的这个 talk，叫做新一代的列约束生成方法。那么 Team 呢，他是香港人，他的普通话不是很好，所以说呢，Team 会用英语来给我们进行这次来做这次 talk。那么大家如果有什么问题的话，也希望大家用英文来提问他。那 Team 应该也可以讲中文，但是中文说的不是很好。如果大家也可以用中文来这个用普通话来提问他。如果需要翻译的话，Team 你让我来翻译就可以
的。对。
好，那让我简单介绍一下 Team。Team 的中文名呢叫做曾文耀Team Man Yu Ting. It's an incoming assistant professor in the Department of Industrial Manufacturing and System Engineering of Texas Tech University starting for 2025. He is currently a PhD candidate in Industrial and System Engineering at Lehigh University under the supervision of Professor Carmel as Shahade. He obtained his BSc and MPhil in the Risk Management Science from the Chinese University of Hong Kong. His methodological research interests and expertise center around data-driven stochastic optimization, which includes proposing and analyzing different uncertainty modeling paradigms and designing computationally efficient algorithms to solve large-scale stochastic optimization models. His primary application areas are financial risk management, healthcare operations research, and transportation systems. His research has been recognized with the Michael Sun Family Best Publication Award winner and the Junior Faculty Interest Group Paper Prize with his advisor Carmel S. Shahada。Team 最近也有一个很好的消息，就是 Team 刚刚又中了一篇这个 Operations Research。那么 Team 呢，也将在这个2025年秋天会加入到 Texas Tech 的工业工程系。那么 Team 也会在新的一年里边招收这个博士研究生，欢迎具备优化数学或者统计背景的同学来申请他的研究生。那么有这个随机优化研究经验者将会被优先考虑。如果有兴趣加入他的研究团队的话，可以把简历发给 Team。那么 Team 的这个联系方式在我们公众号的这篇文章上是有的，是他的这个英文邮件是 myteamthing， 大家可以看一下。曾教授呢也同时欢迎在这个随机优化各方面开展科研合作。欢迎这个大家在发送邮件的时候，在主题标明一下 OR Talk。那么 Team 也就知道是我们从这个 talk 开始，大家可以产生一个交集。好，那 Team 你来共享一下屏幕吧。
好，
好的，
看得见吗？看见。
看得见。好的，
可以，谢谢你。So I will start with English because like everything I did is in English, so it's much easier for me to start with English. But if you have any question you want to ask me, feel free to ask me in Chinese. I will try my best to answer you in Chinese as well. So, okay, so thank you for Zhendong for the introduction. So I'm Manuel Zhang, you can call me Tim, and I'm an incoming assistant professor in fall 2025 in the Department of Industrial Manufacturing Systems Engineering at Texas Tech University. So today's talk is on next generation column and constraint generation methods. So before that, I would like to briefly introduce myself. I think Zhendong mentioned it already. So I will obtain my PhD degree in Industrial System Engineering at Lehigh University and obtained my MPhil degree and bachelor degree in Risk Management Science from the Chinese University of Hong Kong. So my research centers around data-driven stochastic optimization, and there are 3 different lines of research. So the first line of research is about uncertainty modeling. Uncertainty is inevitable in many real-world decision problems. So that's why we often have uncertain parameters in optimization. So this line of research is about how we can leverage data to model uncertainty in optimization models. So this is my first line of research. And the line of research is about decomposition algorithms for solving large-scale optimization problems. With all those advanced uncertainty modeling approaches, the optimization model becomes much more complicated to solve. So we need some computationally efficient algorithms to solve all these models. And this will be like one of the focus of today's talk as well. And my first line of research is about applications. So I propose and analyze different stochastic optimization models to address problems in different application domains, including transportation, healthcare, and finance. I will also mention some of these application works in my talk today. So here is about myself. And now I will move to today's talk, which is about the next generation column and constraint generation CNCG methods. So here is a brief outline of today's talk. So I will first start with the background and motivation, specifically the class of problems that we are interested in and why we are interested in solving this kind of problem. And then in the second part, I will briefly introduce the classical CNCG method to solve the class of problems that we are interested in. And then in the third and fourth part, I will introduce our proposed in-a-set CNCG ICNCG method and the hybrid CNCG HCNCG method. And then at the end, I will conclude my talk. Feel free to stop me anytime if you have any questions. So with this, I would like to first move to background and motivation. So in this talk, we are focusing on the following two-stage stochastic optimization framework. Consider a decision maker that he or she is going to make two sets of decisions in two different time points. So at the current time point, we are going to make what we call the here and now, or the first stage decision. That means this is some decision that you have to make currently, and we use X to denote this set of decisions. And then after a certain time point, we will observe the uncertainty psi right here. And then we are going to make another set of decisions, what we call the wait and see or the second stage decisions. And in this talk, we are going to use Y to denote the second stage decisions. So think about the decision maker at the second stage. When he or she is going to make the decision Y, what he or she can do is to solve what we call a second stage problem. We are going to compute the minimum. So we want to solve the optimization problem that we can find the optimal Y in the second stage. But here we know that the optimal value, we use Q of X psi to denote the optimal value of the second stage problem. Specifically, we note that this optimal value depends on two different quantities. The first one is the first stage decision X, and the second one is the uncertainty psi. And now think about the decision maker now at the first stage. What he has to do is to make decision X, but take into account two different costs. So the first cost is the cost of implementing the first stage decision X, and the second cost will be the cost incurred in the second stage, which is the Q of X psi here. However, as I mentioned, this Q function depends on the uncertainty psi, which is unknown in the first stage. One way to model uncertainty is the following two-stage stochastic programming approach. In this approach, we aim to find decision X that minimizes the sum of the first stage cost plus the expected second stage cost. And this P right here denotes the probability distribution of the uncertainty psi. However, in practice, this true distribution P is often unknown, and one way to hedge against this kind of uncertainty is to use the following two-stage robust optimization model. Instead of minimizing the expected second stage cost, we want to minimize the worst case second stage cost. And this maximum is taken over a set of scenario psi within what we call an uncertainty set, capital psi right here. As you tell from this formulation, this model essentially produces robust solutions that are more robust to the uncertainty here because we are trying to minimize the worst case scenario right here. So the problem here is like a two-stage stochastic optimization framework. And I want to provide 2 examples from some of my previous works to motivate that, okay, this kind of 2-stage stochastic optimization framework is indeed very common. So the first application I would like to mention is the operating room and physiology scheduling problem. So this is a joint work with our collaborators in Columbia University Ivy Medical Center. So in this problem, given sets of surgeries, operating rooms, and anesthesiologists, we want to decide which operating room to open and also assign each surgery to an open operating room and anesthesiologist. And given the sets of surgeries that an anesthesiologist is going to perform and an operating room is going to accommodate, we want to do the sequencing of the surgeries as well as assigning a scheduled start time for each surgery. So in the first stage, we are going to make the integrated allocation, assignment, and scheduling decisions. However, when making all these decisions, the surgery duration is unknown. Indeed, from the data we obtained from our collaborator, the surgery duration fluctuates a lot, even within the same surgery type. So there is some uncertainty within the surgery duration that we have to take care of. And in the second stage, what we're going to do is to make the actual schedule. For example, some surgeries may be delayed. That means it was performed later than the scheduled start time. Another problem I want to share is about the home service routing scheduling problem. In this problem, we consider a service provider that he or she is going to visit customers at different locations. In the first stage, what we're going to make is the combined routing and scheduling decisions. Specifically, we want to decide the route that the service provider is going to travel to different customers at different locations. And in terms of scheduling, we want to give a scheduled start time for each customer. However, when making all these first stage decisions, the travel and service times are unknown in advance. And in the second stage, what we're going to do is to, again, make the actual schedule. For example, the service provider may arrive earlier or later than the scheduled start time. So with this, I would like to go back to our main class of problem, which is the frank 2-stage robust optimization problem. So this problem is challenging to solve mainly because of its minimax structure. As you tell from here, we have the mean normalization over the first stage decision X and an inner maximization problem over the set of scenarios Xi. So before I talk about the solution methodologies, I would like to first make a few assumptions. So the first assumption is that we assume the set of maximizers to the problem. The maximization problem here is finite for any X. So here is just for simplicity at the beginning, and I will talk about that we can actually prove convergence under a relaxed assumption. So in the later part of the talk, I will talk about how we can actually relax this assumption. But for now, for the simplicity, we will just assume that the set of maximizers will be finite. And the second assumption is that this problem has a relative complete recourse, meaning that for any given first stage decision and any uncertainty Xi, the second stage problem Q is often feasible, meaning that we don't have any infeasibility issue in this problem. One thing I want to mention is that although we oppose this assumption, but if this assumption does not hold, then our algorithm can still be applied, except that we have to add some feasibility cut in each iteration if we encounter an infeasible solution. So everything remains the same, but we just need a little bit additional steps to incorporate the infeasibility of the solution if this assumption does not hold. And the third and fourth assumption are just a basic assumption that we make to make sure the problem is well defined, and also we can have a positive optimal value. So this is because we are going to use the relative gap to measure the quality of the solution in the algorithm. But if this assumption does not hold, we can also use what we call the absolute gap. So everything holds if the last assumption does not hold. So we can still use another measure to measure the termination of the algorithm. So before I talk about the algorithm, I also want to make one final connection with what we call the two-stage distributionally robust optimization model. So instead, in the DL approach, instead of minimizing the worst case second stage cost, we are going to minimize the worst case expected second stage cost. And this supremum right here is they can offer a set of distribution P residing within what we call a ambiguity set skirt P here. What I want to make, the connection I want to make here is that for some specific choices of the ambiguity set P, actually we can reformulate the two-stage DL problem into an equivalent two-stage RO problem. So here's one quick example for a moment-based ambiguity set. So in this ambiguity set, we have all the distributions with known mean and with some known moment equality and inequality constraints. And if we use some duality theory, we can reformulate the two-stage DL model to the following two-stage RO model. Essentially, what I want to make is that our solution methods can still be applied to solve all these DL models. Okay, with all this background, I would like to first talk about the classical CNCG method to solve the two-stage RO model. So the CNCG method leverages the following master subproblem framework. In each iteration, we are going to solve two different problems. We first solve a master problem, which is a relaxation of the original RO model, because it is a relaxation of the RO model, which is a minimization model. So the optimal value of this master problem will give us a lower bound to the optimal value of the RO model. And after solving this master problem, we will have a feasible solution. And in the subproblem, we are going to compute the objective value for this given feasible solution, which is the one we obtained from solving the master problem. Because we are evaluating the objective value of a feasible solution, so we can get an upper bound from solving this subproblem. After that, we are going to add new cuts to the master problem to tighten the relaxation of this RO model, and then we are going to resolve this master problem. We will terminate if the gap between the lower bound and the upper bound is small. Now, I'm going to talk about the problems that we're going to solve in the CNCG method. So here is the master problem. It takes exactly the same form as the original RO model, except that we replace the set capital Xi by a finite set S. So here we only have a finite number of constraints right here. And then we solve this master problem and obtain a feasible solution Sj. After that, we are going to solve the subproblem, which is nothing but to evaluate the worst case second stage cost of this given solution Sj. And because we are evaluating the objective value of a feasible solution, so the quantity at the bottom right here is an upper bound on the optimal value of the original RO model. And after solving this problem, we will obtain a potentially new to psi star, a new scenario. So what we're going to do next is to enlarge the set of scenarios S with this new scenario psi star. And then we are going to resolve the master problem with the enlarged set of scenario. So here is very straightforward CNCG method, and it's pretty straightforward to understand. So what is the challenges associated with this CNCG method? For example, we apply the CNCG method to solve one of our DRO model in the operating room and physiology scheduling problem, and we found that when we solve some large-scale problem, this CNCG method could be very slow. So the problem is actually lies in the solving the master problem. So if we take a look in the detail of this master problem, it consists of all the first stage decision X as well as all the first stage constraints. If the original problem has a large number of first stage decision variables and also a very large set of first stage constraints, so the master problem can be very challenging. For example, the scheduling problem we mentioned, we have a lot of binary decision variables and a lot of complicated constraints to model the relationship and also like scheduling decision, sequencing decision, and so on. So solving this master problem to optimality is pretty challenging. So this indeed motivates us to propose an inexact version of the CNCG method, which allows solutions to the master problem to be inexact. So this moves to my next part of today's talk, which is about the inexact CNCG ICNCG method. So this ICNCG method, again, leverages the same master subproblem framework. However, in the master problem, we have a little bit difference. So it looks essentially the same as the one we have in the CNCG method, except for two differences. First, we are going to impose a lower bound on the objective value of this master problem, which is L bar right here. I will mention in a second how we are going to update this L bar. And the second difference here is that instead of solving the master problem to zero optimality gap, we are going to solve this master problem inexactly to a relative gap of epsilon and pj. So we can be 2%, 5%, anything in the beginning, and this gap will be adaptively changed in the algorithm. After solving this master problem, we will record the best feasible solution we obtained, and also a lower bound Lj and an upper bound Uj of this master problem. And we have one additional step, that is to check if the Lj, the lower bound we obtained, is strictly greater than the lower bound L bar we impose. So this is indeed a certificate of a lower bound validity. If this is true, then we are going to set a algorithmic parameter curly L here to the current iteration J. So with this certificate, we can show that curly L in this algorithm is always a lower bound, valid lower bound on the true optimal value of our model. And after that, we are going to update the L bar that we are going to use in the next iteration with the upper bound Uj. With this, we are going to solve the subproblem, which is exactly the same as what we have done in the CNCG method. So we will obtain an upper bound U bar. But we cannot simply repeat this algorithm, the steps in the CNCG method, because we introduce inexactness in the master problem. To ensure the convergence of this inexact CNCG method, we need some mechanism to correct the inexactness we introduced in the master problem. So the mechanism we introduced is what we call the backtracking routine. So in this backtracking routine, we are going to compute two different quantities, the actual relative gap and the inexact relative gap. The actual one is computed based on a weighted upper bound U bar and a weighted lower bound L curly L. And the inexact one is a proxy of the actual one by using the upper bound of the master problem Uj in place of the weighted lower bound or curly L. What we're going to do next is to check if the actual gap is smaller than the specified tolerance epsilon. If yes, then we are happy with the quality of the solution, then we terminate. Otherwise, we will do one of the following steps. We check if the inexact gap is smaller than some parameter epsilon tilted. If yes, then we perform the exploitation step. The idea here is that we are not able to terminate because the actual gap is still very large, but the proxy of this actual gap, the relative gap, actually shows that we don't have a lot of space here. So that means we introduce too much inexactness in the algorithm. So we need to correct the inexactness we introduced to the master problem. So therefore, in this exploitation step, we are going to go back to that equation, curly L, that we have the most recent weighted lower bound, and we are going to reduce the master problem relative gap epsilon j mp by a factor alpha less than 1. So what we are doing here is going to shrink the relative gap of the master problem after we reach the exploitation step. Otherwise, if the inexact gap is still very large, then we can indeed perform the exploration step, which is nothing but to enlarge the set of scenarios as in the classical CNCG method. Note that this epsilon tilde here indeed controls the frequency that we visit exploration step. So it's like a parameter that we can control the frequency that the algorithm proceeds to these two different steps. So here is a quick summary of this entire ICNCG method. So the colored box here are those steps that are additional to the classical CNCG method. First, we are going to solve the master problem, and then we have a tiny step which updates the security L parameter, which keeps track of the validity of the lower bound. After that, we solve the subproblem and we obtain an upper bound. We then check if the actual gap is small enough. If yes, then we terminate. Otherwise, we check the intersect gap. If it's small enough, then we go to the exploitation step and reduce the master problem relative gap. Otherwise, we go to the exploration step and enlarge the set of scenarios. One thing I want to mention is that our ICNCG method is indeed a generalization of the classical CNCG method that I introduced in the beginning. Specifically, if we choose all the relative gap of the master problem to be 0, then all the lower bound we obtain from solving the master problem will be valid. So we don't need this query L to keep track of the validity of the lower bound. And we also do not have what we call the intersect gap anymore. So this entire algorithm reduces to the classical CNCG method. So with this, I would like to talk about some theoretical guarantees and the philosophy behind the design of our algorithm. So the first proposition I would like to show is that every time when ICNCG reaches the exploitation step, then the actual relative gap is upper bounded by some quantity here. So this is a little bit hard to see, but here if we can do an expansion, then we can tell how these upper bound look like. So it is essentially a sum of the epsilon tilde, which is the H parameter which controls the exploration steps, plus those relative gap of the master problems. So that's why in order to achieve the convergence, like we want the actual relative gap to be small enough, when we reach the exploitation step, we do want to reduce the relative gap of the master problem so that this upper bound can be reduced. So that's why in the design of our batch tracking routine, once we go to the exploitation step, we want to reduce the relative gap of the master problem. And with this, under the same assumptions adopted in the classical CNCG method, which is in this Zheng and Zhao's paper, we can prove the finite convergence of the ICNCG method. In particular, if this epsilon tilde is chosen small enough, then these ICNCG methods can terminate in a finite number of iterations. So I would like to quickly show you the sketch of the proof, which is a little bit straightforward to tell. So we have two different steps, right? If the ICNCG does not terminate, it will either go to exploitation or exploration step. So for the exploration step, every time we go there, then the scenario set is enlarged. And we also know that by our assumption that there's only a finite number of maximizers to the subproblem. So that's why we could only have a finite number of exploration steps. As for the exploitation, because we know that every time we go to exploitation, we are going to reduce the master problem relative gap. And the upper bound on the actual gap is given by the following from the previous proposition. And if this goes indefinitely, then this converges to the quantity. And by assumption of this epsilon tilde, then we can show that this quantity will always be strictly less than epsilon, which is the gap that we want at termination. So that's why we will only have also a finite number of exploitation steps. So this concludes that the entire ICNCG method would terminate in a finite number of iterations. Now, I want to also mention that our ICNCG method is flexible and users can tailor our algorithms for their specific application problems. So in the paper, we propose two different variants. The first one is the exploitation frequency variant. Specifically, we are going to impose what we call an exploitation frequency, meaning that if we do not proceed to the exploitation step for a sufficiently long time, then we force the algorithm to proceed to the exploitation step. The advantage here is that we can remedy the situation that the valid lower bound information is not exploited for a pretty long time. If we exploit that, we can probably have a better lower bound of the algorithm, so it actually improves the overall convergence. Another variant that we actually use in the experiment that I'm going to show you next is the foreign time limit variant. So in this variant, we are going to impose a time limit when solving the master problems. And every time when we proceed to the exploitation step, we are going to increase the time limit as well. So the advantage of this variant is that we could potentially escape from solving some very challenging master problem at initial iterations. You can imagine that at the very beginning, the set of scenarios is actually very small. So solving the master problem exactly will not give us a very tight lower bound. So we won't want to waste the computational resources to solve those challenging master problems. And this is how the time limit variant could be beneficial. So with this, I would like to show you some numerical experiments on a distributionally robust operating room scheduling problem. So in this problem, given sets of surgeries and operating rooms, we want to make the following two sets of decisions. We want to decide which operating room will open and assign each surgery to an open operating room. So here is a quick illustration of this problem. Suppose we have 5 different surgeries on the left and we have 3 different operating rooms on the right. For example, we may decide to open the first 2 operating rooms and assign the first 2 surgeries to the first operating room and the remaining 3 surgeries to the second operating room. And in this problem, the uncertainty will be the surgery duration. Here is a quick look at the model. So we have 2 main objectives. So we're going to minimize the fixed cost of opening the operating rooms plus the cost of the overtime cost. And again, this overtime cost is random because the surgery duration is random. And we are going to use the DLO approach to model uncertainty in this problem. Specifically, the set of distribution we want to hedge against is what we call the mean absolute deviation ambiguity set, which consists of all distributions with non-mean and mean absolute deviation less than or equal to some parameter ui. What I want to recall here is that using duality theory, we can reformulate this 2-stage DL model to a 2-stage hour model so we can apply our CNCG methods to solve. We generate 5 different instances with different combinations of the number of surgeries and operating rooms using some publicly available surgery data sets. And we have a total of 60 different instances right here. So in this plot, we show the time performance profile for different algorithms. Specifically, it shows the percentage of instances that an algorithm can solve within a given time. In this plot, the blue line corresponds to the ICNCG method, and the yellow line corresponds to the CNCG method. The bottom line means we solve the problem to a 2% gap, and the yellow line means we solve the problem to a 5% gap, the solid line. As we could tell from this figure, that our ICNCG significantly outperforms the CNCG method. Specifically, it could solve a larger number of instances and can solve the instances within a shorter amount of time. We can also take a look at the instances that the algorithms were not able to solve to a 2% gap within 2 hours. You can see that in these settings, the ICNCG method actually terminates with solutions that have a gap which is most likely less than 10%. However, if we apply our CNCG method, the classical CNCG method, when we terminate, then the relative gap at the end could be pretty large, could be more than 80 or even 90%. The reason is that the master problem of this surgery scheduling problem is actually very difficult to solve, and the CNCG algorithm allocates a lot of time for solving some initial master problems, and that's why at point termination, the overall relative gap remains very large. And this shows the benefits of using our ICNCG method over the classical CNCG method. So with this, I would like to conclude this ICNCG method. And now I'm going to move to another session, which is about the hybrid CNCG method. So I will first tell the story. Is like, so after proposing this ICNCG method, we're trying to solve some facility location problem. And we actually found that even though we use our ICNCG method, some instances could still be very time consuming to solve. That means we need to, the instances are very hard to solve using the ICNCG method. So this motivates us to think about actually, could we improve the algorithm not only by modifying some of the parameter settings and so on, but to significantly improve the algorithm by changing some of the optimality curves using the problem structure. So the exact problem structure that we would like to leverage in this specific session is the following continuous recourse with right-hand side uncertainty. So that means that in feasible set of the second stage problem takes the following form. So we are essentially have linear constraints, linear in psi, and it's just like independent of x and y. So this is what we call continuous recourse with right-hand side uncertainty. And indeed, many problems like scheduling problems or like the facilitation problem that I mentioned, the second stage problem often have this kind of structure. What we like to first recourse is that the primal optimality cut in the classical CNCG method that we talked about in the previous part. Every iteration, so we are going to have this kind of optimality cut in the master problem. Specifically, we are going to decompose the set of Kasai because we only impose this constraint for a subset of Kasai, of the capital Kasai. And because Q is a minimization problem, then we can write this constraint into the following form by introducing primal second stage variables and constraints. So that's why we call this the primal optimality cut, because these are the primal second stage variables and constraints. So this actually makes us to think about, okay, can we actually leverage some dual information as well of the second stage problem? So one intuitive way to think about that is to consider the dual of the second stage problem. So in the second stage problem, which is a LP here, we have a very specific structure. So we can take the dual of this LP. So we can write it as a maximization problem over the dual variable pi. And we denote the set of dual feasible solutions as this capital pi. So with this notation, we can rewrite the worst case second stage course using this format. And if we only have a subset of the dual feasible solutions pi, then this obviously would be a lower bound to the original worst case second stage cost. This indeed motivates us to decompose the set of the second stage decision variables pi. Accordingly, we have what we call the dual optimality cut as follows. So we have the delta greater than or equal to the maximum over the scenarios of the dual objective of the second stage problem. Of course, this constraint itself is nonlinear because it has the maximization problem. But if we have some structure of these uncertainty sets capital Xi, we can reformulate these into a set of linear constraints. One example I wanted to give here is the polyhedral uncertainty set, which is pretty common in the literature. If this is the case, then we can use the duality theory to reformulate the maximization problem into a minimization problem. Then we can reformulate this entire dual optimality cut into the following set of constraints, which involves the dual variable and constraints of this maximization problem. So the idea of this hybrid CNCG is more or less straightforward. So we incorporate both the primal and the dual CNCG cuts in each iteration of our ICNCG method. Then this becomes the new hybrid CNCG method. Again, under some assumption, we can show that the hybrid CNCG method terminates in a finite number of iterations. So here, actually in this paper, we actually prove the convergence in a more general form. So I would like to talk a little bit about the convergence analysis here. So the finite convergence of the algorithm follows directly if one of the following conditions hold. If the set of the maximizers to the problem is finite, which is something that I assume in the beginning for simplicity. So if that's true, then we have the finite convergence directly. Or another assumption is that the set of optimal dual solutions is finite. So in our setting right here, our recourse problem is an LP. So the second condition always holds. So that's why we always have finite number of iterations, finite convergence of the algorithm. However, in some settings, we may not have these two assumptions hold. So what if they do not hold? So could we say something about the convergence as well? So indeed, yes. So we actually prove the convergence of this type of decomposition algorithms in a more general sense. So consider that in each iteration, we impose the optimality cut of the following form, delta greater than equal to some Q function, X and C. And this Q X function satisfies the following condition. It takes suprema over C and it recovers the worst case second stage cost. For example, if in the dual optimality setting, the C could be the pi, which is dual feasible variables, and the Q would be just the dual objective value function. So if this is true, then we can also prove the finite convergence that if the Q function here is uniformly linearly continuous over C. So how this result generalizes the existing ones. So consider, for example, the primal CNCG method, which is something that I talk about in the third part of my talk. So the convergence is typically proved under the assumption that the set of the maximizers to the subproblem is finite. However, in some settings, it may not be true. For example, if the set uncertainty set capital Xi is not polyhedral or is not finite, then this assumption may not hold for the primal CNCG method. However, our convergent analysis can still be applied to show the finite convergence of the CNCG method if the cut we are going to impose in each iteration is uniformly linearly continuous. So this is how we actually generalize the convergence results of the existing literature. Okay, with this, I'd like to show you some numerical experiments showing how a hybrid CNCG method outperforms those classical CNCG methods. So this is the facilitation problem that I mentioned I motivate for the HCNCG method. So in this problem, given a set of candidate facilitations and demand occasions, we want to decide which facility to open. So the first stage decision is to decide which facility to open. So here is a quick illustration. We have multiple facility and multiple customer. And here, for example, those who are circled, the facilities that are circled, they are open facilities. And the second stage, we are going to assign customers to open facilities. In this problem, the uncertainty will be the customer demand. Here is the DL model that we're going to solve. Again, it consists of two different objectives. The first one is the opening facility cost. And the second part is the worst case at the second stage cost that I'm going to mention in a second. We use the DL approach, the model uncertainty, and in this experiment, we use the mean support ambiguity set, which consists of all distributions with no mean. In the second stage problem, we want to make the assignment decisions by minimizing the sum of the transportation cost and the unmet demand penalty. We generate different instances. So here are two instances for illustration, so with different sizes of the number of facilities and number of customers. And we have in total 36 different combinations of the parameters, like the fixed cost of opening facilities, the facility capacity, and the unmet demand penalty. So the figure here again shows the time performance profile of different algorithms. So the red one corresponds to the hybrid CNCG method. The blue one corresponds to the dual CNCG method, where we only use the dual optimality cut. And the green one corresponds to the primal CNCG method, which is the classical one. As you can tell from this figure, our hybrid CNCG method dominates the DCNG method and the pre-CNCG method. That means our hybrid CSCG method could solve a larger number of instances and solve instances within a shorter amount of time. We could also take a look at specific instances, the exact solution times from different algorithms. So here we have 8 different combinations of the parameters, and the bars here show the solution times in seconds. We use the same color code as before. The red one corresponds to our proposed hybrid CNCG method. It's very clear that the solution time we take to solve the problem with hybrid CNCG method are significantly shorter than the primal or the dual CNCG method. For example, in this specific instance, we were not able to solve the instance within 2 hours using primal or dual CNCG method. But if you use our hybrid CNCG methods, we could solve it within like less than 500 seconds. These results demonstrate the superiority of our proposed hybrid CNCG method over some classical CNCG-based algorithms. So with this, I would like to conclude my talk today. So to summarize, we propose first a new index-set CNCG method that effectively addresses the computational issues associated with solving the master problem. Specifically, we do not allow solution to the master problem to be exact. And then to address the index-setness we introduced in solving the master problem, we indeed develop a backtracking routine that could balance the computational gains and inaccuracies from solving the master problems inexactly. And after that, we actually leverage the structure of the second stage problem of some problems to propose what we call the hybrid CNCG method, which incorporates 2 different sets of optimality curves, the primal and the dual optimality curves. We derive theoretical guarantee for our hybrid CNCG method and the index-set CNCG methods, in particular for the finite convergence. We also demonstrate the flexibility of our ICNCG method. Finally, we also demonstrate computational gains of our proposed CNCG methods over those in the existing iteration. Okay, with this, I would like to thank again everyone for joining today's talk today. And here on the right bottom corner, I show 2 QR codes, which are corresponding to 2 different papers. One is the index-set CNCG method in the third part of my talk, and the right one is the hybrid CNCG method, which is a preprint currently. Thank you again for attending my talk, and I'm happy to take any questions if you have, and I can answer in both English and Chinese, depending on what you want. Thank you.
Okay, thank you, Tim. 大家有没有什么问题？大家有问题的话，可以直接在那个聊天框里边贴出来，然后我们可以来问一下 Tim。那么 Tim， 你这个 email 可能要改一下，左下角的 email。
也可以改一下。那你可以在那个 chat 里面写一下，或许
OK， 我
在这里
复制一下 chat，
可以。
然后我有一个问题，先问一下。
可以。
那么在你的第30页 page 30，
第30多？
第30页。
30这里的。
你的 ambiguous set 你是用的这个 mean support 对吧？所以它是有，比如说对于那个 standard deviation 那些有要求吗？这是还是我的意思是就是它，你先说。
我是说这里没有 mean absolute deviation， 就是只有 mean 的 information。对，我之前用的，譬如说那个 operative room 那个问题，就是前面的那个问题，就是用那个 mean absolute deviation， 就是对那个 mean absolute deviation 是有要求的，但在这里是没有，就是说我要一个 fixed mean。对，
那也就是说这里的这个 DJ 它的分布也是没有要求的，它可以是 uniform log normal。
对，就是我们没有什么要求的，只要它的 mean 和 support 是 match 的话，那就可以了。对
，OK，
对的。
我把你的那个 email 再给他们听。
可以。我想说，就是一般来说，就是那些 DRO 的 ambiguity set 也没有什么，就是对那个 distribution 有要求。一般就是，譬如说 moment based 的话，就是你说有一些 moment constraints，比如说 mean constraint mean absolute deviation constraint 或是什么 dispersion constraint 这样子，就是一般来说很少就是说那个 distribution 是 uniform 或是 Gaussian 什么什么的。对，
哎，你好，Tim。
哎，你好。
哎，你好，我想问一下，就是你这个你提的这两种算法，它的子问题都是线性的，有没有可能说对于那种零一的，就是整数子问题，它这个 CCG 算法还可以适用吗？
对，其实让我等我一下。对我们这个问题，譬如说你 x 是01的话，其实没有问题的，因为是我们没有动那个 x。其实，那譬如说在 master problem 里面，就是可能会比较难解一点，就是譬如说 x 是 binary， 对吧？所以就是我们要 propose 那个 inexact method， 就是让我们不用解到 exact， 对吧？就是如果 x 是 integer 或是 continuous 或是 binary， 其实没有什么问题，就是那个 framework 可以也可以用。你就是说，譬如说 y 是 binary， 那个 framework 也可以 apply， 但就是说，譬如说那个 subproblem 怎么解的话，那就是另一个问题。就是我们 propose 那个 framework， 譬如说 ICNCG， 我是说 ICNCG 里面那个 framework 可以就是直接用的。但问题是，譬如说那个 subproblem 怎么解，那你就要看那个问题的 structure。譬如说，如果 y 是01，那个 subproblem 那个 max min problem 怎么解？那你要再看那个有没有 subproblem structure， 你可以利用，然后 reformulate， 让你可以解那个 subproblem 这样子。但这个东西我想说，就是譬如说 hybrid CNCG 的话，那我们是要利用那个譬如说这个problem structure， 就是 continuous recourse， 就是那个 second stage decision 的话，那不可以是01，就是要 continuous。但我觉得其中一个 future direction 就是可以想想，譬如说，如果 second stage problem 其实是有01或是有 integer decision 的时候，那我们可不可以就是 generalize 那个 hybrid CNCG 那个 framework 去解那些问题？那这个我觉得还可以，就是算是一个 future direction 吧。就是如果 y 是01的话，但如果你是说前面那个 inexact CNCG method 那个 framework 本身是无论你那个 x 或是 y 是01，那个 framework 本身还是可以用的，只不过是你怎么解那个问题，就是 subproblem 是 master problem 的方法可能是有点不同。我可以解，对，你说。
其实最近我看了一些相关的这种论文，其实目前好像是有一两篇这种论文可以求解，当 y 是01的时候，也可以用这个 CCG 这个框架来做，好像。
对的，那个时候是也是可以，就是其实本身CNCG这个方法就是 y 是什么也可以解的，就是那个问题的重点就是我说的那个 subproblem 怎么解是问题，因为这里因为是你解的是个 max min 问题，其实如果 y 是一个01的话，那理论上这个问题就比较上难解一点。所以我看就是譬如说有人就是想，譬如说如果有什么 specific structure 的话，你可以容易解一些啊，就是那个 subproblem 可以容易解一点，就是他们想方法去 improve 那个 solution approach for the subproblem 这样子吧，我可以说。对，那我想说就是这个 framework 本身也可以用，但就是解那个问题本身可能有点不同。对，
是的，就是他们好像对这个子问题的求解设计了一些，比如说类似于 branch and cut 这种来求解一下，好像。就是这个，我是最近稍微了解了一下这个问题，因为我之前用过你这个 ICCG 算法，就是效果非常好。
谢谢你。对，也有些是的，我也看过是 branch and cut， 就是用另一个 framework 去解，是可能 nonlinear 的，好像是 nonlinear 什么也可以。
对，是的，
就是对，有点不同吧，我是说。
对，我之前给你发过邮件交流过这个 ICCG 算法，当时我有个地方好像有点报错，当时给你发过邮件，你当时给我指出有个地方需要加一个非常小的常数，然后就可以解决那个问题了。不知道你还记得这个邮件吗？
我记得你我记得原来是你。
对，
对，我记得。对，我可以说一下，就是其实就是在这个 step 里面 LJ 大于 L bar， 因为其实这个就是你知道，就是因为是 strict equality， 就是你用 譬如说 computer 解的话，就是
嗯
这个 comparison 的话，那可能有些 floating error，就是可能他们是 theoretically 一样，但就是 numerically 算起来是不一样，就是一些 floating point error。所以我们可以做，就是在那个 L bar 可以加一个很小的 small epsilon，比如说1e-6的这些东西，那就可以让它正常的运算，对，这样子。
对，当时就是对加这个常数以后，这个算法效果就非常好了。因为不加这个常数的话，有时候它可能这个下界会比上界稍微高一点点，就是有时候它会报错这个。
对，那这个是 implementation 的时候是有一点要注意的地方。
行，
感谢你提出这个问题。
我后面再学习一下你这 HCCG， 我对这个算法比较感兴趣。
可以，感谢你。
行，到时候有什么问题我再给你发邮件请教你。
可以啊，随便。
好，谢谢 Tim。
谢谢你。
好，我们看一下还有没有那个问题。我把 Tim 的这个邮件发在了那个聊天框里，大家可以给 Tim 发邮件。
对，我还没有我 test 的邮件，很不幸 ，unfortunately， 所以我还是用不厉害。
对 Tim 可以介绍一下，就是你可能要在什么时候招博士生，还有对他们的这个要求或者怎么样？
可以啊，我可以简单
说。Tim 是一个在我眼中是一个非常厉害的 rising star， 对吧？他在博士期间有2篇 operations research， 我觉得他非常厉害。所以
感谢你。
所以如果有同学想读 Tim 的博士的话，我一定是非常的鼓励他们去读 Tim 的博士，因为真的可以学到很多，包括从 Tim 平时的交流。虽然我们的研究方向不太一样，但是从 Tim 和 Tim 的交流当中，还是可以学到很多东西。感谢你。
对，我可以说一说，就是对我在招新的博士生，就是可以是，比如说 Spring 20，就我觉得 Fall 2025有点赶吧，就是可以 Spring 2026，或是 Fall 2026也可以。就是我还是有一个学生可以招的，就是如果你对我做的 research 有兴趣的话，你可以就是发一个邮件，随便问我一些东西，或是对，如果你想交流或是做 research 有交流的话，我也是欢迎你们就随便给我发邮件的。对 ，I'm open to any collaborations。对。
你好 ，Tim， 我想问一下，你的第2篇论文也是关于这种算法设计的吗？就 OR。我看过你第1篇 OR 是关于那个手术室问题的吗？
对，第一个是关于手术室。对。
那第2个也是类似的吗？
你说 OR paper 吗？
对。
我第一个是 Confess Fairness Paper，Confess Fairness Measure， 就是你在那篇文章里面，就是简单来说，就是我们 propose 一个 unified framework or Confess Fairness Measure， 就是在 literature 里面有很多不同的 fairness measure， 就是 measure 那个 fair 有多 fair， 一个 decision 里面有多 fair， 譬如说 Gini deviation 呀，譬如说那个什么 range 的等等，对。然后，但他们就是有很多不同的模式等等，然后我们就 propose 一个 general framework， 就是把它们都归类成一个 Confess Fairness Measure， 然后就怎么说，用那个就 propose 一个 general framework， 然后说 OK 有一个 axiomatic characterization， 就是我们有一些 actions， 然后就是 action 就 characterize 那个 class of Confess Fairness Measure。其实就是一些 convex analysis 的东西，然后我们用那个 framework， 然后也去 propose 一个就是solution method， 也是用 CACG 的，但就是我们那个 framework 本身就是可以把那个 fair measure 写成一个 robust 的东西，然后我们就有个 min-max structure， 所以我们就可以用 CACG 的方法去解那个问题，就是用一个新的角度去解那个问题，然后我们发现就是给一些原有的 direct reformulation 跑的就是时间比较好一点，而且我们也做了一些 stability analysis 的东西，用那个 framework， 对，就是比较不同的，对。
行，我后面学习一下。
好，随便看看，感谢你。
我直接把这篇发在聊天框里，应该是这篇。Collect fairness measures。
对 ，conversation。
Tim， 我想问一下，你这边会收访问学者这种吗？就是类似于联培的学生吗？
这个我在想，其实我没有定，就是譬如说你想做 research，就是我 start up 就是怎么说，就是没有一些 summer internship 的钱是给一些就是 summer intern 的，但如果例如说，譬如说你想就是一般给我做 research 去学习或是一起交流一下，那我是可以的，对。
好的，好的，好的，好，谢谢 Tim。
好的，感谢你。